Onto you. You're picking up so you can look at and laugh at everyone else's pain. Happy Tuesday. Exciting moment we've all been waiting for, your exams. If you have not done so already, make sure you pick up an exam before you leave today. Exam is 10 questions. I was going to make it longer, but I got lazy. I was going to do 15. I was going to make it 3 times a test. Figure it's final exam. Have to. I got question 10, and I'm just like, I don't feel like doing any more solutions. So I just stopped at 10. Categories cover everything we've done this semester in no particular order. It was up to the RNG gods. And then, of course, I reviewed some of them because some of the questions the RNG gods picked were just ridiculous. It should be converges. Just for when I use this again. Right. If you have any questions for clarification, do not hesitate to reach out, ask me. Right, you'll do all of the work right on here. I did print it single-sided, so if you need to go on to the back, go ahead. Just make sure that you mark that your work continues on the back and clearly label the work, so I know what problem it goes to. Goes without saying, make sure that I can read your work. Obviously can't grade it if I can't read it. You can also do some work on loose leaf paper. Just attach all of your scratch paper at the end. And again, just, mark on the test, on the exam, that there's more work on the scratch paper, and clearly label your work. Notes, textbook, other official course materials, any model calculator, except for the problems where I tell you you're not allowed to use a CAS. I don't remember how many there were. 2 tops, maybe. You cannot discuss this with anyone. Unlike the tests, this work will not be put on OneNote. So it's just going to be graded right on the paper, and then you won't ever see it again. Unless you want to make an appointment with me. Over the fall. When I'm back on campus. Must be turned in at the end of our final exam period, which is 2nd of May, 7 p.m. I will be in this room from 5 to 7. So I will be here for the scheduled time. If you want, you can also just come in and use that time to finish up. Make sure you print your name as well as sign. And again, make sure that it's printed legibly so I'm not guessing whose it is. Include first name and last name. Most importantly of all, as always, have fun. I sure did. Remind me. There it is. We plotted that, right? At the end of last class? Okay, good. Yes. Yes, I need the hard copy. I will not accept it in any other form. A couple more plots to look at. First one is called the nephroid of Freeth. It's given by the polar equation r equals 1 plus 2 sine of theta over 2. And so remember, we use the polar plot command. This allows us to plot functions of the form r equals f of theta. I'm just going to write out theta. There are actually 2 ways you can get the theta command itself. Hit escape, theta, escape, or you actually could have seen it. What is that, a forward slash? Forward slash, bracket, theta. And it's going to close it out automatically because it had a bracket. I'm just too lazy to always go through all that, so I'm just typing out theta. They didn't give us a domain 0 to 2 pi. Sounds good. Oh, that's right. That's going to give me the same ones unless I set the seed. Oh, good. I think I know why. Getting something that looks different. Right, so that's 0 to 2 pi. There's 0 to 4 pi. And then after that point, it stays the same. Oh, yeah, I guess that makes sense. It's theta over 2, the period would be 4 pi. Duh. All right, so there's the plot. Again, I believe we discussed last time we can turn on the polar axes, but it doesn't really give us too much useful information, so we typically don't. This one is actually pretty cool. So they want 0 to 10 pi here. I'm gonna have some fun. Sine of 2, 3 theta. Let's go 0 to n times pi. All right, I'm going to let n shift from 1 to 10. So we'll do it pi, 2 pi, 3 pi, 4 pi, 5 pi up to 10 pi and see how that affects it. So there it is for pi. So that would be at for the 0 to 10 pi. Yes. Some of this very last part here, it's just the manipulation part. Let's go up to 20 and see if that makes a difference. Go so fast doesn't give itself time to really load in. I don't really see a difference between that and 10. There isn't any. But I think 9 is different, isn't it? Yeah. 9 isn't quite complete. 10 is. All right, so it's not going to change from 10 pi on. Which is a shame. It means it's going to start going over itself. Does look the same. Yeah. And so again, you get some pretty cool curves from Polar as well. Oh, look at that. Any questions on polar curves before we move on to calculus? So for the sake of time, I may just not worry about the plots. And so what we'll do is we'll just find the tangent lines at the given points. Well, we can think of a polar curve as a parameterization. But R is a function of theta. So it becomes f of theta cosine theta, f of theta sine theta. Well, we know how to find dy dx of parameterizations. Be dy d theta over dx d theta, right? Dy d theta, product rule. F prime times sine plus F times cosine. Dx is also a product rule. F prime times cosine minus F times sine. The tangent line would then be given by y equals y naught be at some point theta naught, so just plug in theta naught for c, right? And that's how you get f of theta naught times sine of theta naught. Plus slope times x minus x naught. X naught is f of theta naught times cosine of theta naught. Right. These are the two that we're going to be using. Treating polar curves as parametric curves, right, of this form, makes what we're doing now an extension of what we did with parametric calculus. Right, so really, this isn't going to be new. Dy dx. It's going to be f prime of theta, so the derivative of 1 plus sine theta, which is cosine, right, times sine. Plus 1 plus sine times cosine. Then it's going to be f prime times cosine minus f times sine. Numerator, we'll simplify 1 plus 2 times sine times cosine. I'm sorry. Let's strip the cosine through to the 1. cosine plus 2 times sine times cosine. So cosine plus sine of 2 theta. Cosine squared minus sine squared. Cosine squared minus sine squared. Cosine of 2 theta. The denominator can simplify to cosine of 2 theta minus sine of theta. There's our derivative dy dx. When theta is 0, we get y equals 1 plus sine of 0 times sine of 0 plus cosine of 0 plus sine 0 over cosine of 0 minus sine of 0 times x minus 1 plus sine of 0 times cosine of 0. Right. All I'm doing is plugging 0 in as theta naught. Sine of 0 is 0. That first term is just 0 then. That becomes 1. X minus 1. So there's the tangent line when theta is 0. Now when theta is pi, one plus sine of pi times sine of pi plus cosine pi plus sine of 2 pi over cosine of 2 pi minus sine of pi x minus 1 plus sine pi times cosine pi. Zero. Negative 1 over 1. X minus 1 times negative 1. Negative x plus 1. That's the tangent line at pi. One more for tangent lines. Polar curve, R is cosine of 2 theta. We're going to do it at 4 points. 0, pi over 2, negative pi over 2, and pi. F prime. Negative 2 sine of 2 theta. Times cosine. No, times sine, right? Times sine. Then it's just plus F times cosine. This is where it's times cosine. Then minus cosine of 2 theta times sine of theta. Gonna go ahead and factor a negative out of the denominator. I actually could just distribute that negative through the numerator, couldn't I? I'm going to do that. I can write it that way. Two sine of 2 theta times sine of theta minus cosine of 2 theta times cosine of theta over 2 sine 2 theta cosine theta plus cosine 2 theta sine theta. I mean, we could use identities on that. Sine of 2 theta is easy, so that's not too bad. Cosine 2 theta, you have double angles. Cosine squared minus sine squared. 2 cosine squared minus 1, or 1 minus 2 sine squared. They don't really simplify, right? Those 2 involving the cosine of 2 theta would then become 2 terms instead of 1. That's not simple. So I'm not going to do that. We could also do product to sum. I do not think that's going to simplify it either. That would give us 4 terms in both numerator and denominator instead of the 2. Unless there are some cancellations that happened. Which I'm not sure if there are without actually doing it. So, I'm just gonna leave it. There's dy dx. At 0. Gonna be cosine of 0 times sine of 0 plus 2 sine 0, sine 0 minus cosine 0, cosine 0 over 2 sine 0, cosine 0 plus cosine 0, sine 0 times x minus cosine 0, cosine 0. That's a problem. Why is that a problem?
Equals 0.
You think? Only 90? That's sad. That's sad. That denominator is 0. Sine of 0 is 0. Huh. That means our line is not in the form y equals mx plus b. We have a vertical line. The question is, where is that vertical line located? It's going to be located at the x coordinate. What does that evaluate out to? Oh dear. Oh, this is not good. It's cosine of 0. What's 1 times 1? Vertical line is at x equals 1. So that's our tangent line. Let's do pi over 2 next. Be cosine pi times sine pi over 2 plus 2 sine pi over 2 minus cosine pi over 2 over 2 sine pi over 2 cosine of pi plus cosine. I'm sorry, I did that backwards. That's pi. So sine pi, cosine pi over 2, and then cosine pi sine pi over 2. X minus cosine of pi cosine of pi over 2. What's sine of pi? What's cosine of pi over 2? The question is our numerator going to be 0? Our denominator going to be 0? No. Well, this term is 0. This term is non-zero. We have 0 slope. Tangent line is then a horizontal line. Cosine of pi times sine of pi over 2 is what? What's cosine of pi times sine of pi over 2? -1. Tangent line is the horizontal line, y equals -1.
So our functions are equals cosine 2 theta, right?
Yes.
So if we plug into that pi over 2, we get when theta is pi over 2,
R is equal
radius is
to
1.
technically it's -1.
Why is it -1?
Well, what is cosine of 2 times pi over 2?
Oh yeah.
Right. So what you want to be careful because yes, technically the radius would be -1, which sounds really wrong. Which is why I don't like thinking of it like this. I prefer to think of it this way, but yes. Technically you have r equals -1 there, which is allowed, by the way, in polar coordinates. It's just not something I like. So I always think of radius as a positive value. Right, but yeah, so at pi over 2, you'd have r equals -1. So r of pi over 2 is -1. Does that make sense? Which again is allowed. You're allowed to have a negative radius in polar by definition. Let's do negative pi over 2. The cosine of negative pi sine negative pi over 2. Actually, in fact, I'm going to cheat. Euler blessed technology. The only thing that's going to change is all of those become negative, right? But cosine is even. Sine is odd. So that becomes negative. That stays positive. That doesn't change. This becomes negative. And that becomes negative.
We could just say that the function has a period of pi.
The polar function does.
Yes. So when we shift theta by pi, it should keep the same tangent line.
Doesn't. Right, because you're thinking of right, you're thinking of that, but not in terms of its rectangular curve. Right, so you're treating this already as rectangular. And it's not, it's polar. So when you plot it on the rectangular coordinate system, it's actually a flower. Right, so this is actually, if you plot it, it looks like this. Here was theta equals 0. Here was theta is pi over 2. Up here is actually theta negative pi over 2.
Oh, I see. I see now.
Right, and then this would be obviously pi.
The function is periodic, but we're
Right.
it still changes.
Right, so the function, it is periodic, but when you go to rectangular, it doesn't quite match up the way you're thinking. Right, so the rectangular function itself is not necessarily periodic. Right, so you want to represent, again, it's not really a quote unquote function, right? It's a relation. This is still going to clearly be 0. -1 times 1 times negative. We now have the tangent line y equals 1. And then finally, at theta equals pi. We're going to have cosine of 2 pi times sine of pi plus 2 sine of 2 pi times sine of pi minus cosine of 2 pi cosine of pi all over 2 sine of 2 pi cosine pi plus cosine of 2 pi sine of pi times x minus cosine 2 pi times cosine of pi. We have a problem again. That denominator is 0. which means our tangent line is vertical. But where is it located? Just that evaluation. -1. So the tangent line is x equals -1. Actually, I might call this a four-leaf clover. This curve, because that's what it looks like. They do call each of those a petal, though. I don't know what they would call the whole shape. Oh boy. Now the fun begins. Finding the area of polar regions. This becomes so much easier in Calc 3. Yes, Calc 3 does make some things easier. We don't have that luxury, though. Area is going to be 1/2 the integral from alpha to beta of f squared of theta d theta. F of theta is the polar curve. Alpha and beta are the rays that the region are bounded by. So here we go. I did that. We had 2 cosine of theta. And then we had 2 sine of theta. go or theta goes 0 to 2 pi. Expressions. I can't do fulfill. That is a bastard. Uh-oh. There we go. Perfect. That's what we're going to find the area of. We want to determine the ray of intersection. All right. It's clear that that is where they intersect. So they intersect on that ray. Question is, what is that ray? Right. They also happen to intersect on that ray. And that ray is easy. That's theta equals 0. Determine where they intersect. Well, you just do the same thing. Set them equal to each other and solve. It means tangent of theta is equal to 1. So what's theta? There is another. Pi/4 as well. But we can clearly see we don't need 5/4. However, that only gives us half the area. So we're just going to double the answer. right? Since we're looking at, oh, actually, no. So we need to determine which circle we want to be in. Well, since we're integrating here, that lower curve that we're using, which is part of the circle, 2 sine theta. Use reduction identity on sine. Integral of 1 is going to be pi over 4. Minus 1/2 sine of 2 theta. Now that gets the value from 0 to pi over 4. Becomes sine of pi over 2 minus sine of 0, which is just 1. Our area is pi over 8. No, it's not. I think I'm multiplying by half. Area is pi over 2 minus 1. Or pi minus 2 all over 2. Either one. Shared by the cardioids. 2 times 1 plus cosine theta and 2 times 1 minus cosine theta. I'm going to use the same code. That's the area we're looking for. This doesn't really require any shenanigans. This area is going to be bounded by the raised 0 and pi over 2. This area, pi over 2 to pi. This area, pi to 3 pi over 2. This area, 3 pi over 2 to 0. Furthermore, these areas are perfectly symmetrical. So this area equals that area. This total area has to equal this total area.
You don't have to deal with that in this problem, but what do you do when you think your radius might be negative? Like, do you have to check if it is?
It shouldn't matter.
So even though your bounds of integration would be off by some, it would still work.
It shouldn't because of how you set up the raise. Right, so it really shouldn't matter if your R becomes negative. Right, because your raise, the way you set up the bounds for the raise will fix that. Put it this way, I've never run into that scenario that became an issue. But I typically deal with this kind of area in double integration. Right. So I would set this up as a polar double integral because it's a lot easier that way. And you don't have to worry about it either because it's not going to be on a test. I know that for a fact. It's not on the test and it's not on the final. Which is sad news, right? Very sad. So let's just find the area of this little piece here and multiply it by 2. Or I'm sorry, multiply it by 4. So it'll be 4 times a half, 2. Integral from 0 to pi over 2. Hope this gives me what I want. It should. Wait a minute. No, it should. We're going to find out. Curve we're dealing with. Is this one, which is 2 times 1 minus cosine of theta. 1 minus 2 cosine of theta plus cosine squared. Eight times the integral from 0 to pi over 2 of 3/2 minus 2 cosine of theta plus cosine of 2 theta. Off to a good start. This integral will be 3 pi over 4 minus 2 sine of theta from 0 to pi over 2. All right, just minus 2. Plus a half sine of 2 theta from 0 to pi over 2, which is 0. Six pi minus 16, which is the right answer. So yes, I am allowed to do that. So glad that worked out nicely because I really didn't want to have to set up 2 integrals. This one's cool. Inside the lemniscate, r squared equals 6 cosine of theta, and outside the circle, r equals √3. Huh? That's not the picture that should have been pasted. Oh, I guess it is. Okay, whatever. We are inside the lemniscate, but outside the circle. That's the area we're trying to find. This area and that area are the same. So if we just calculate this area and double it, we have the total area. But this area and this area is the same. So if I just calculate that area and double that, then I have that area. So we will calculate the area between those rays and quadruple it. Well, that ray is clearly theta equals 0, right? So we're fine there. We need this ray. So what we need to do is determine where does the circle and the lemniscate intersect. Right, so you could do that, or since this is already r squared, just square that and then set them equal to each other, right? Same thing. Either way, you're going to wind up with 6 cosine of 2 theta is 3, meaning that cosine of 2 theta is 1/2. That means 2 theta is what? Which, well, technically no, because that only gives you one solution and there's more than one. But that's a good starting point.
Where do
What is the inverse cosine of a half?
Where do you get 2 theta from?
Because that's a typo. That's supposed to be 6 cosine of 2 theta. Dead. I plotted it right. Otherwise, I don't think that's a lemniscate. Just a circle, I believe. Oh dear. Inverse cosine of 1/2. Makes me sad. And I already handed out the final. Damn. If I'd covered this before, I could go back and change it to add more problems with trig.
I think it's pi/3, but that doesn't really look pi/3.
pi/3. Remember, this is for 2 theta, not theta. But that's not the only place. Right? Technically, your solution is solution set would be pi/3, 5 pi/3, 7 pi/3, or 11 pi/3. Right? 2 theta would have to be theta has to be between 0 and 2 pi, so 2 theta is between 0 and 4 pi. Then you just divide those by 2. Of those 4 solutions, only one of them is quadrant 1, and that's pi/6. Which means we're only going to take 2 theta to be pi/3, because that's the only angle that we're interested in. That means this would be 11 pi/6. This one is 5 pi over 6. And then that one would be 7 pi over 6, right? Yeah, 7 pi over 6. Right, so those would be the 4 rays that completely bound this region. But again, we're only calculating one and quadrupling it. So it'll be a half times 4, which is 2. Integral from 0 to pi over 6. Now we have a conundrum. Between these rays, we are bounded by 2 polar curves, not just one. So it's going to be the difference of the 2 squares, right? I don't think that's right. I think it should be the other way. Oh, no, never mind. Yeah, that's right. Larger curve minus smaller curve. Yeah.
So why don't you square them first and then subtract?
For the same reason we did that with shell method. Not shell method, disk method, washer method. Right, the area of 1 would be r squared. We're doing a difference of the areas. Right, so it'd be the integral of the first r squared minus the integral of the second r squared. So when you combine them,
You'd be squaring first and then.
right, that's exactly what I did.
Oh, yeah.
Right, we already have r squared as 6 cosine of theta, so that was easy. And then r root 3 to square that 3. And then d theta. This is a nice integral. No voodoo math. Six cosine theta integral 6 sine theta from 0 to pi over 6. Well, sine of 0 is 0, so we're just going to have 6 times sine of pi over 6. What's sine of pi over 6? Oh, wait a minute. Right, that should have been 2 theta. So it'd be a half times sine of 2 times pi over 6, which is pi over 3. What is sine of pi over 3? That's 3 root 3 over 2. Minus, now just 3 from 0 to pi over 6. Pi over 2. Just wrote that out wrong. So minus pi. And that would be the total area. And sad news, you don't have any polar areas on the final exam or test 4. Unless my memory is really shot, because I don't remember writing up solutions for it. However, this does look familiar, so I think you are going to do a problem like this on the final. Length of a polar curve. I vaguely remember doing an arc polar length integral for the final. So we're going to find the length of the polar curve, 1 plus cosine of theta. That means we need one full period, which is just 2 pi. Arc length of a polar curve. I'm running out of time. I have time to do this one problem, and that'll be it. Integral from alpha to beta of the square root of f squared plus f prime squared d theta. Which again shouldn't be too difficult to find if you do. Remember, we did the arc length of a parametric curve. Polar curve is parametric. So you just plug in x equals r cosine of theta, y equals r sine of theta, and then use the parametric equation to derive this. Zero to pi. Square root of f squared, so 1 plus cosine squared. Then it's plus the derivative squared. I leave you to plug this into a calculator. After the algebra, that boils down to the integral 0 to pi of the square root of 2 plus 2 cosine of theta, which is 8. So this quiz actually doesn't have to do anything with the problem set we were just working on. It has to do with the previous problem set. So it's a fairly simple quiz. Shouldn't take long. I am also going to post the 4th test. Figure out a due date when I post it. Thinking of making it due Monday at 11:59. That we don't have 2 tests due on the same day. This is also the last quiz If I hadn't mentioned it, I plan on only taking the highest 20 grades for the quiz. So 3 of them will be dropped.